There we go. Okay, so just I'm going to say it one more time, right? Just so that the recording has it, since I forgot to hit record, right? We learned that Newton's first law was the law of inertia, right? Where things that are stationary or things that are not moving tend to stay not moving, right? And the things that are moving tend to stay moving. So that's the law of inertia. The second law was F equals ma, which is the force equals the mass times the acceleration, right? You can also use that for things, objects that are falling. So that's F equals mg, right? Mass times gravity this time. And then that brings us to Newton's third law of motion, which is for every action, there is an equal and opposite reaction. And so other ways of saying it, of course, are whenever an object exerts a force on the second object exerts an equal and opposite force on the first object. And so you can also say action equals an opposite reaction, or mathematically, you can say that F equals, excuse me, you can say that F equals minus F1 equals minus F2, or you can even talk about it via the talking about it like in terms of masses, right? Because F equals ma, you can say that the first mass and the first acceleration equal the second mass and the second acceleration to the negative, right? So those are just different ways of saying all the same thing, okay? So again, looking at this little equation here, F1 equals the minus F1, right? So examples of this would be, for example, jet propulsion. Exhaust gases are in one direction, and the rocket goes in the other direction, right? So the rocket's literally going towards, say, the moon or something like that, if you were like Apollo 13. But then the propulsion from the rocket engines is actually pushing out the other direction. So you can see that there's an opposite reaction, right? One, here's the rocket going this way, and the propulsion is going this way. Does that make sense? Going the other direction, okay? Uh, this can also be seen in gravity here. You jump from a table and you accelerate to the earth, but in reality, both you and the earth are accelerating towards each other, right? You never really think about it that way, right? But like if you're falling, right, not only are you falling, the earth is also coming towards you too, right? So it's an equal and opposite reaction, okay? You, a small mass, has a huge acceleration. The earth has a huge mass, so it has a very small acceleration, right? But it still means that the first mass and the second mass, right? I'm sorry, the first mass and the first acceleration, you falling towards the earth, right? And then is still equal to the negative of the mass of the earth and the acceleration of the earth. Okay, and it makes sense, right? Because if you're small, you can get up speed faster, you can accelerate faster, right? But if you're super big, right? How fast compare like a motorcycle accelerating to like a Mack truck, right? Like an 18-wheeler accelerating, right? What could accelerate faster? The motorcycle, because it's much smaller than an 18-wheeler, right? So that's what they're talking about there. Okay. So your very first question for today is here. Which of the following describes Newton's third law? I always try to keep your very first question simple. Simple and easy. Do you need me to take a picture of you for it, Carly? Wow. Did you get an upgrade on your phone? It was a warm day today. Otherwise, I would have worn a hoodie that said Cont on it. But you told me that last week too. You said it wouldn't get cold again until Wednesday. So yeah, so I'll wear a Colts hoodie on Wednesday. Make myself even less professional looking than I already look for unprofessional, you know? Okay, let's see what everybody has said on this thing here. Of course, I have to log in again, and I was just here earlier today, so I don't know why. Ah, here it is. Okay, we have 20 people in here, right? Do we have 20 people? Now we have 21 people. Okay, so That last slide literally had all the answers on there. So the vast majority of you got that correct. That's good. I'm very proud. But yeah, all these are all ways of describing. All these are ways of describing Newton's third law, right? For every action, there's an equal and opposite reaction. Action equals opposite reaction. The force uh, one equals the negative force two, or the mass acceleration one equals the negative mass two and acceleration two. Okay. Okay. So I'm talking and I hear people talking. What is going on here? Do not speak when I'm speaking. We are having a lecture, aren't we? If you want to talk, go outside. All right. So, other things to take note of when we're talking about Newton's laws, right? The friction on tires provides the necessary centripetal acceleration, right? So, when a car is trying to, turn, okay, when a car is trying to turn, the the uh, the friction of the tires on the road help it turn, right? That's why it makes that turn there. But the thing to notice is that there is people inside the car, and the car may be turning, but they're really, if these people aren't wearing like a seatbelt or something, right? These people are flying to the side, right? How many times have you ridden with me before and you feel like you're just going to fly out the side window? My girlfriend says that all the time because I take very crazy turns, right? And she's wearing a seatbelt. But these people aren't, so they're being pushed up against the side because they're still going straight when the car is turning to the left. The car is turning to the left, right? So passengers continue to go straight ahead in the original direction, right? As the car turns, the door comes toward the passenger. Which is the first law, right? The car turns, and you push against the door, but in congruence with the third law, the door actually pushes against you equally, right? That's why the door is able to stop you. Okay, if the door wasn't if the door wasn't able to push against you at an equal force as you are pushing against it, you would fly out the door, right? That's that's the third law in action right there. Okay, that's the third law in action. So Newton's law of gravitation. Okay, man, Newton had so many laws. Okay, gravity is a fundamental force of nature. Interestingly enough, after all this time, we still don't really know what causes gravity, right? But we can only describe it, right? And so Newton's universal law of gravitation says this. It says every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay? And I'll show you what that means in just a second. I'm going to let people write some stuff down. Okay? I'll show you what that means in just a second. So, I think everybody stopped writing. Let's answer this real quick question about gravity. What is not true about gravity? What is not true about gravity? Oops, wrong one. I'm glad someone caught that. I'm glad someone caught that trickiness that I did there. Tricky, huh? Okay, so wow, it was actually a mixed bag here, right? Because a lot of people actually picked all these statements are true, but in fact, the one that is not true is B, because we do not know what causes it. Remember, yeah. See, we do not know what causes it, right? We do know what causes it, right? And like I said before, I mean, it's been a couple hundred years since we knew, no, more than that, maybe 500 years, and we still don't know what causes gravity. So that's a little crazy. Okay, so just to talk about this, the universal law of gravitation, I want to show you this equation, right? Okay. So here's the universal law of gravitation's equation right here, right? It's F equals the gravitational constant, right, which is that number right there, okay, times the mass of the first object times the mass of the second object divided by the r here, which is not radius, it's the distance between the two objects, okay? It's the distance between the two objects, okay? So the thing that I want you to notice about this particular formula here is that in the law it states, right, that the force that, every particle attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance, right? So remember the directly proportional part and then the inversely proportional part. Directly proportional to their masses, inversely proportional to their distance, right? So if you look at this equation describes that relationship because notice that force is here and both masses are where? At the top, right? So as the force gets bigger, the mass gets bigger. Or as the mass gets bigger, the force gets bigger, right? On the other hand, though, as the distance gets bigger, right, since it's in the bottom, it's in the denominator, right? Yeah, that's why it's an inverse relationship, okay? It's an inverse relationship, okay? As the distance gets larger, the force gets smaller, right? So that's what I want you to see. I'm not going to particularly make you do make you do math with this equation, but I want you to see how the law that Newton came up with says directly proportional to their masses, inversely proportional to the square of their distance, is borne out completely by the equation here, right? As force goes up, mass goes up. As mass goes up, force goes up. On the other hand, if force goes down, radius goes up. Or the other way around, if radius goes up, force goes down. Make sense? Know the difference between inversely proportional and directly proportional, okay? So G here, this big gravitational constant, it's a very, very small number. It's it's 6.67 times 10 to negative 11. Wow, that's like 6 with like 10 zeros in front of it. So it's a really small number, okay? It's thought to be valid throughout the entire universe, and it was measured by Cavendish. By Cavendish, I don't know who Cavendish is. Some guy was measured by Cavendish 70 years after Newton's death, and is not equal to G. So the big thing about this is that the little g here is the 9.8 meters per second squared. Remember that? That's the little g, 9.8 meters per second squared. That's the gravitational acceleration, okay? But big G here, right? Big G is this number, 6.67 times 10 to the negative 11. Very small number. Okay, very small number. So let's take a look at this conceptually now, right? Here's the equation again, right? Here's the distance between them here, right? And here is the force that they are both acting against each other with, right? Okay, and notice here, remember I was telling you a while back that we have these arrows that show a vector force, and when they're the same size, that means it's equal to each other, right? But it's not just equal to each other, it's actually equal but opposite to each other, right? Because this force is going this way to the right. This force is going to the left. So this one would be the negative side right here, okay? That would be the negative side, right? And then of course, again, r here is the distance between the two particles, right? And so r here could mean like the distance between me and the crust of the Earth, or the distance between the moon and the Earth, or the distance between the moon, between the sun and the Earth, right? All that stuff can be r. But the important thing to remember though is that r in this equation is not the radius. Sometimes it can be the radius, but in this equation, it's specifically the distance between the two different masses, okay? Specifically the distance between two different masses. So here's a sphere, right? And we always think of the gravitational force being at the center of the sphere. And here's me right here, right? And I'm the mass 1, right? And then mass E here is the mass of the Earth, right? And then, on Earth we use weight, and weight equals your mass times the gravity, right? That's why if you go to the moon, it's completely different. It's much smaller. It's 1/6 the gravity, right? And you notice here that the Earth here is exerting the same amount of force on me as I'm exerting on it, on the Earth, right? So for a sphere that's homogeneous, the gravitational force acts as if all the mass of the sphere were at its center. Okay, right? So this is a very simple concept. You just got to remember that the Earth is pushing on you right now, right, as you're standing here, right, or sitting there, the same amount that you're pushing on the Earth, right? Equal and opposite. Or I guess it would be equal but opposite, right? Okay, so your next question. What does the R represent in the gravitational equation? What does the R represent? Let's see how people are going to answer this one. Anybody have any problems logging in? Really? Glory, what's wrong? Oh my God. Well, Gloria, I need you to send me an email to tell me you're actually here today. Because when you answer these questions, that's how I take attendance. Okay? So you have to tell me you were here. Otherwise, I'm going to go through the list of people that have answered questions, and if your name's not there, I'll mark you absent. Okay? That's why it's important for you to. And then the other thing about it too is that it tells me exactly what time each person puts in an answer, right? So I can tell if you left early or not, or you got here late, right? So it's a very easy way for me to figure out what the I lost my train of thought again. Oh, what your attendance status was. What's your attendance status? Okay, so let's see here. Earth's gravity. No, that's not the one we're looking for. There it is. 20 responses. Let's see if everybody was paying attention to me. Again, the vast majority of you did pay attention to me, right? Because the answer is the distance between two particles. Exactly. It is actually the distance between two particles. I literally just said that in the previous slide, right? So if you missed it, I don't know how, but I did. I literally just said that. And most of you did get it right, so good job. Good job. So let's take a look at Newton's law of gravitation in this little example here. Okay, in this little example here. I have two objects, and one of them is 1.0 kilograms, and the other one is 2.0 kilograms, right? They are 1 meter apart, right? They're 1 meter. Well, I wonder why that M should not be italicized. Sorry, it should just be a regular small m. But they're 1 meter apart, right? What is the magnitude of this the gravitational forces between the masses, right? What is the force between right here? Okay, between these two, right? So, uh, of course, we have the distance, right? We have our two masses. We have, and then we have, that's actually all we need, right? We actually don't need the gravity at all because the equation doesn't even ask for that, okay? So to do this problem, right? Okay, it's actually very simple, right? All we have to do is we use this equation here, okay, that we just talked about. And the G is that gravitational constant, that's 6.67 times 10 to the 11, right? And then we put the first mass, which is 1 kilogram, the second mass, which is also is 2 kilograms, right? And then we divide it by the distance, the square of the distance, right? And it's that easy, okay? And then that's going to be your answer, 1.3 times 10 to the negative 10, okay? So I mean, that's as probably as straightforward as it's going to get, right? Because you have the two masses, mass one and mass two. Then you also have the distance they are apart, right? And that plugs everything in. And then you have G there, right? Which is the big G, which is that 6.7, 6.67 times 10 to the negative 11. So if I ever ask you a question about this kind of equation, literally that's how I ask it, right? I will give you the formula, the first of all, and then it will have the two masses, it will have a distance. I will also give you this constant, right? Like in a formula sheet, okay? And then all you have to do is figure out what the force is, okay? Simple math. Nothing crazy, I promise. So we can also do this thing here too, where we talk about the force of gravity on Earth, and the equation is almost the exact same, because we had mass 2 here, right, as being the two masses. But if you're talking about another object with the Earth, all you have to do is change the mass 2 to the mass of the Earth, right? To the mass of the Earth. Whew. Okay. So, and then here the r is going to be the radius of the Earth, and the reason why is because remember when we saw that picture of that guy, which I called myself, on the Earth a second ago, right? Right here. Even though r here, little r means the distance between two objects, it turns out since the Earth is a circular object and you're standing on top of the Earth, the first object being you, the first mass being you, the second mass being the Earth, and the Earth is a circle, we still get a radius, right? So sometimes the distance can be a radius. Not all the time, but if the object is circular, then the distance can be a radius. There we go. Okay. So this force is just the object's weight, right? Which is W equals mg, which we talked about that before, right? Your mass times the gravitational acceleration that you have on Earth, right? And so interestingly enough, right? You can actually cancel out the first masses, right? You can cancel out mg here, or not mg, but m here, and that m there. Both those masses can cancel out, right? And what it shows you that is that gravity is independent of mass, right? And so that's actually a mathematical equation that shows you that regardless of what mass is, if you drop an object that's really big, high mass, and an object that's really small, right, from the same distance, they will fall to the earth at the same rate and hit the ground at the same time, right? And that's why that is. It's because when you do this equation here, and you cross out, you cancel out mass there, and you cancel out mass there, right? It shows mathematically that you can do that, right? So a lot of times in physics, what happens is that a physicist, right, will see something happen, like in the world, literally, right? A physicist sees two objects falling, right? One that's 1 gram and one that's 1,000 grams, and then he or she sees them hit the ground at the same time, and he's thinking to himself, what kind of equation can I come up with that will describe what I just saw, right? And so this is the equation that came up when they saw that, right? They took together they put together what Newton already had, right, for F equals ma, and they took what's the guy's name again? Cavendish, 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 whatever his name is, all that stuff, right? And they put, thank you very much, because I couldn't remember his name. They put it all together and they figured out that, hey, putting together Newton's law, right, F equals mg, and putting together Cavendish's constant, and then canceling out the m's actually makes it so that we can describe mathematically that a small object and a big object being dropped from the same height will hit the ground at the same time. Crazy, right? They didn't even have computers back then. It's unbelievable. All right, so here's your next question. Ooh, I was getting parched. I was getting a little bit like excited there. And I'm not even a physicist. I'm a chemist, and I think this is really crazy stuff, right? Like, how did they come up with this stuff? Okay. So I just went on a very long rave about this. So rave is the good one, right? Or is it rant? Rant or rave? Is rant bad? I think rave is good. So I was just raving about this question, or this what we're talking about right here in this question. So hopefully everybody gets it right. Do, 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 do. Wow, everybody already did it, right? Okay, good. Exactly, right? 18 out of the 23 picked mass. Yes, mass is the thing that gets to be canceled out right there, right? Mass is the thing that gets to be canceled out, and that explains why things can fall and hit the ground at the same time, even though they're different masses. But as long as they are at the same height when they fall, they'll hit the ground at the same time. Oh, and also I can't forget neglecting air resistance if there's no air resistance, right? So here we have an astronaut, right? And she's floating in space. Okay, she's floating in space. So weightlessness in space is the result of both the astronaut and the spacecraft falling to the Earth at the same rate, right? Isn't that crazy? So really, you could be like in an airplane, right? Oh, actually, have you ever? So I used to live in California in this place called Orange County, and like on Laguna Beach, if you know where that is, that's where I used to live. And they have very specific, literally very specific, like sound ordinances. So you can't have any loud noises before 8 o'clock, for example, right? In Orange County. And so when I was flying out of Orange County one time, and it was before 8 o'clock, the pilot comes on the plane and says, "Hey, we're about to do our tandem takeoff. If you're not sure what this is, you're going to feel weightless for a while, right?" And so what happens is that they'll take off, right? But when the plane takes off, it really has to burn its engines really loud, like really strong, for it to take off when the plane takes off. But since you can't do that because it's really loud, what they do is they call it a tandem takeoff, where they'll burn it for a couple seconds and then they'll let go of the gas, basically, and they'll burn it for another couple seconds and let go, and they do it until they get out of Orange County airspace, right? So it's a good 5 minutes of them. And so what you're feeling is basically the plane goes up and then comes back down, and then goes up and then comes back down. And so while it's on its way down, you literally feel yourself lifting out of the chair. It's crazy. It's absolutely crazy. So those Orange County types. Have you ever seen the show Laguna Beach on MTV? It's exactly like that, like quite literally. Unbelievable. Anyway, so you can't be, maybe you can, maybe if you want to be an astronaut, you can't experience this if you go up into space, right? But you can also experience it in just in a plane. Because if a plane is crashing, not crashing, but like going downwards, right? All right. While it's going downwards with no propulsion pushing it up, you're floating in the air and you're lifting out of your chair just like you would on a on a spacecraft. Oh, another good example. Um, Roller coasters. Whenever you're going on a downturn of a roller coaster, don't you feel yourself lifting out of the chair of the roller coaster, right? Of the cart? Good thing they have those like seatbelt things, otherwise you'd fly off and die, right? And so that's another good example of that. Okay. Oh God, I hate roller coasters. I really hate roller coasters. Okay, so another thing that is plays into this stuff, right, is called buoyancy. Okay, buoyancy force is the upward force resulting from an object that is wholly or partially submerged in fluid, right? Like a boat, right? A boat is buoyant, it floats, okay? And that boat floats based on this principle, Archimedes' principle, right? An object immersed in a fluid experiences a buoyant force equal to the weight of the volume of the fluid that was displaced. Okay? All that means is that a boat sitting and floating in water has displaced the same volume of water, right, that is equal to the actual boat itself, right? Equal to the boat itself, right? See, back in the 1300s and the 1400s, all these smart people, right, were coming up with all these principles and laws and theories and stuff, but they really just describe like normal everyday things, like obvious things, right? But since they said it first, they become famous, like Archimedes. You know, you say that today, and you're like, who cares? Like you weren't the first one. So both liquids and gases are considered fluids. Okay, things can float in air as well. Things can float in air as well. And just to take it a little further with buoyancy here, right? The buoyant force depends on the weight of the fluid displaced. The weight of the fluid displaced depends on the density of the fluid and the volume displaced, right? So what an example of that would be is the fact that if you have salt water, it's going to be much denser than fresh water, right? And so I think it's called is it the Dead Sea that's in Europe? And it's like really salty, like super, super salty, like saltier than the ocean salty, right? And you as a person can just float on top of it, right? Because it's so dense, right? But if you were to be in fresh water, I mean, technically you could float too, right? But like, I mean, you're really feeling like you're on top of the water with the salt water, right? Um, I guess you could think about it like this: say you have drowned, right? And there's no more air in your lungs. Your body sinks to the bottom, right? But if you were at the Dead Sea and you drowned and all the air was out of your body, you would still be floating. Does that make sense? Right? I actually drowned once before. It's not a fun thing. It's not a fun thing. They had to do CPR on me and everything. Coughed up all this water, you know, because my uncle, he's a bad parent. My uncle is, or a bad, babysitter. Anyway, I'm getting flashbacks, like trauma here. Okay, so ships float because the average density of the ship is less than the water, right? That it would displace. Okay, which is basically the same thing as talking about liquids that have a density that is less than water, right? For example, oil. What happens to oil when you put it in water? It floats, right? Same thing. So oil, I just said this. Oil floats on water because it's less dense than water. Cream floats on milk since cream is less dense than milk, right? And then also submarines can uh, make themselves more buoyant too by pumping in and out water, right? By pumping in and out water. That's what submarines do. Okay. So next question: which of the following is an example of buoyancy? Oh, we're doing really good on time here. Doing really good on time. It's probably because it's not math heavy anymore, right? I don't have to go through and like do examples of different problems. Do you guys appreciate that I've made it less math heavy? I mean, really, the only math that was supposed to be in this class, like consistently, is just doing the unit conversions and stuff. After that, it was really learning about the concept. So it just felt like it was super math heavy, but that was the only chapter that was supposed to be that math heavy anyway. You know? Okay, so that was yes, buoyancy. There you are. 19 responses, still waiting for a couple more. There they are. That was fast. And yes, the vast majority of you again answered correctly. This time I did not trick you, right? I did not trick you. The answer, in fact, is D, because all of these are examples of buoyancy. Okay? All these are examples of buoyancy, right? Let's keep on talking about some movement here. We got momentum now, right? We've got momentum. And momentum is quite literally the mass times its velocity, right? And so for short, we usually use the small p, the lowercase p, and that equals mv. So momentum equals mass times the velocity. Okay? That equals the mass times the velocity. We have a system of masses in linear momentum sorry. If we have a system of masses, the linear momentum is the sum of all the individual momentum vectors, right? So here we have the final momentum equals the initial momentum, which makes sense, right? But then you can also say that one momentum is equal to this momentum here is equal to all the other momentums together, added together, right? If you have more than one. the sum of the individual momentum vectors, right, equals a single momentum too. Okay. But the thing that I want you to know, the thing that I want you to remember is this equation here. I mean, you don't have to remember it because I'll provide it to you on an exam. But the thing that people deal with the most is the P equals mv part. Okay. I will never present you with a problem that has multiple momentum vectors because I don't even know how to work them myself. Why would I make you work them, right? Just kidding. I know what I'm talking about. Just kidding. I mean, it may seem like I'm winging this, which I am winging it, but I think I wing it pretty well. Okay. All right. So there's another law. So many laws here, right? The law of conservation of linear momentum, right? And again, this is like an extension of the first law, where things will stay in motion, right? Things will stay in motion. So blah, blah, blah. Law of conservation of linear momentum. The total linear momentum of an isolated system remains the same if there's no external or unbalanced force acting on the system, right? So it's almost exactly the same as Newton's first law, right? An object in motion will stay in motion unless acted upon, right, by another object, right? It's almost the exact same thing. So linear momentum is conserved as long as there's no external forces, no external unbalanced forces, right? An unbalanced force is basically a force that's one side is stronger than the other side. So if it has to be an unbalanced force for it to disturb the linear momentum. Otherwise, it's going to be just like the first law. It just keeps on moving in the same momentum, same direction, blah blah, and it does not change with time. Does not change with time. Okay, does not change with time. So if we take a look at this guy here that's jumping off of this boat to the rocks, which I don't know if that's the safest thing to do, right? We have we have a conservation of linear momentum here, right? Because I mean, I've jumped off of many boats. I'm sure you have too, right? But when you jump off a boat, you go forward. But what else happens? The boat goes backwards, right? Like the boat, like if it's a rowboat, if it's if it's like a motorboat, then it's not gonna go. I mean, it could if it's not on, but the thing is, the point is, right, that when a person jumps off the boat, it has to they have to put force on the boat, and so they'll go forward, but the boat, since it's sitting on this very frictionless water right here, will go backwards, right? So there you can see then that the momentum here, the initial momentum, is equal to the final momentum, right? Because both of these momentums are the same, right? It turns out that there is zero momentum for both the man and the boat, right? Because they're both moving back and forward at the same rate. Okay. When the man jumps out of the boat, he has momentum in one direction, and therefore so does the boat. Their momentums must cancel out, must equal zero, right? I'll tell you what, if the boat didn't move because of friction or something like that, the man would get further, wouldn't he? When he jumps, he would get further. But since he's on a boat and there's very little friction on water, that's why the momentums are the same. Okay. Oh, I keep saying the same, but the same and opposite, right? That's why they cancel out. Okay. So expect on your exam these kinds of questions where I'm asking you about these scenarios, right? And tell me what would be able to answer the question what would happen, right? So one of the things I could say is, what if this boat was stuck in ice and the man jumped, right? Would it still be equal momentums? No, right? The man would have more momentum because the boat stayed where it was, right? So that's the kind of questions that you should be able to answer, right? Not necessarily with numbers and doing math, but just know what would happen in different scenarios. Okay. So your next question: which of the following is not true of the law of conservation of linear momentum? The total linear momentum is an isolated system that remains the same if there's no external balance force acting on it, right? What the heck? Where's D at? Oh, whatever. It's conserved as long as there is no external forces and it does not change. It does change with time. So which one is? There should be uh, a all of the above are true, but that's okay. I'll give you a hint. That's not the answer. All of the above are true. It's not the answer since it's not showing up on the screen. Okay, and that was linear momentums. Linear momentums. Okay, 14 people have responded. 19 people have responded. Oh, good job! The vast majority of you caught it this time, right? It does not change with time, right? And this one says it does change with time. So the answer is definitely C there, okay? Linear momentum does not change with time, okay? So the untrue statement is C, okay? The untrue statement is C. Good job. I'm very proud, very proud, very proud, super proud, okay? Right, so let's apply some yes, let's apply some linear momentum, okay? If I have two masses and they are on a frictionless surface, which I don't know how like a 2 by 4 piece of wood is like frictionless, but whatever. Let's say they're frictionless, and they when stringed together, right? The string is going to be weightless. Okay, the two masses fly apart when the spring between is released, and the velocity that they go, right, is 1.8 meters per second. Okay, well, the velocity for the first one is anyway. Okay, and so let's talk about this one more time. There are two masses that are at rest on a frictionless surface, right? When a string is burned, the two masses fly apart due to the release of a compressed spring. So there's a compressed spring right there, right? The first mass's velocity is 1.8 meters per second squared. I mean, sorry, 1.8 meters per second, right? You can already tell by the picture that this one's going to be slower, right? Because look at the arrow, right? The vector there looks smaller than that one, doesn't it? Right? You can already tell that it's going to be smaller. Okay. So if you're given, right, all this information here, 1 kilogram, right, for mass one, 2 kilograms for mass two, velocity one is 1.8. How do you solve for uh, velocity two, right? How do you solve for velocity two? And then the thing about it is that 3, maybe 4 slides ago, I gave you all these different ways of thinking about momentum. And one of the things you could do is m1v1 equals negative m2v2, right? So you can plug in m1 there, v1 there, m2 there, and then just solve for v2, okay? So that's super simple because now you just put in the 1 kilogram there, 1.8 meters per second there, divided by the 2 kilograms, and you get a negative 0.9 meters per second, right? Which makes sense because number one, it's negative because it's going the opposite direction of the other force right here that's going positive, right? And if you didn't already know that, if things are going to the right, we consider that being positive, right? Because that's going forward. If things are going to the left, that's considered going negative, right? And then we also know too that the velocity is going to be smaller. But the interesting thing to notice here, right, is that um, you have the 1 kilogram mass, right, and it's at 1.8 meters per second squared. I'm sorry, meters per second, right? But then you have the 2 kilogram mass there, right? What is its velocity? It's zero point 0.9. So it's half of what that would be, right? So this mass was twice this mass in mass, right? In kilograms, but the velocity was what? Half of the other one. Does that make sense? Right? Do you see that relationship there? Right? Mass 1 was 1 kilogram. Mass 1 was 1 kilogram. It had a velocity of 1.8 meters per second. But then mass 2 was twice the mass of mass 1 at 2 kilograms. And its velocity was half, right? So does that make sense? The kind of relationship you see there, right? Cool stuff, cool stuff, cool stuff. All right. So, talk about jet propulsion again here. I don't know why we're going back to this, but that's okay, right? Jet propulsion can be explained in both terms of Newton's third law and linear momentum, right? We have that one I was talking about before, where we have the first momentum equals the opposite, the negative of the second momentum, right? Then also the mass 1 times mass 2, sorry, mass 1 times velocity 1 equals the negative of mass 2 and velocity 2, right? So the exhaust gas molecules have a very small mass, right? But they have a very large velocity, okay? Very large velocity. Makes sense because the molecules are super small, right? Remember that? Things that are really small have a very fast velocity. They don't have as much weight that they have to, overcome to get fast velocity, okay? Think about that. Think about that motorcycle versus the 18-wheeler thing again, right? Okay? The rocket has a large mass and a smaller velocity, right? So it turns out that all these things equal out from each other, right? If you have a small mass and a large velocity, it gets canceled out by having what? A large mass and a small velocity. Does that make sense? Right? And that's why momentum is conserved. Okay? That's why the rocket can go somewhere, right? That's why the rocket can go somewhere. Dang, I'm on a roll today. This is good stuff right here. Good stuff. Okay, so there's another thing called angular momentum. Okay? And angular momentum is just the momentum that goes around in a circle. Okay? So L here, big L here, right? Big L is angular momentum. That equals the mass times the velocity times the radius of the circle. Okay? Also, since the circle goes around in a circle, right? There's not really a left and right, but it just goes around in a circle, right? L1 will equal to L2, right? So that's different from angular momentum. I mean, not angular momentum, linear. That's different from linear momentum, right? Because linear momentum had this being negative right here, right? Remember that? But in angular momentum, it's not negative. Why? Because the circle doesn't go left or right when you turn it, does it? It just goes in a circle, right? It just rotates. And that's why L1 and L2 equal each other, right? That's why the mass, the velocity, and the radius of the first one also equals the mass and the velocity and the radius of the second. Okay? So the thing I want you to notice here, because I might ask a question about this, right, is why is it that on angular momentum right here, right, not angular momentum, sorry, linear momentum, right, we have negative for the second momentum, right, and the second mass and velocity, but we get here, whoops, ah, but we get here, and there's no negative. And the reason why is because when you're going in a linear fashion, you can go left or right. But if you're a circle, you're just going around in circles, right? You're not going left or right. And that's why there's not a negative there. Okay? So your next question is this. What is the formula for angular momentum? Man, we might actually get through all these slides today. I wasn't expecting that. I guess that's how it goes when I'm not doing like example problems over and over and over, like multiple of them. Okay, let's see how people are answering here. This should be an easy one. Should be an easy one. 18 responses so far, 20 responses. Woohoo, look at that. I love it when it's all the same color. Good job. Good job. Wait, is this all the same color? Yes. Good job. Awesome, awesome. That is true. The letter A there, choice A, is definitely the formula for uh, angular momentum. This is Newton's second law right there, right? F equals ma, and then F equals mg is gravity. So good job, good job. Awesome, awesome, awesome. All right, next, right? In talking about angular momentum, since we're going around in circles, we've got to talk about torque, okay? We've got to talk about torque. So torque is the twisting effect caused by one or more forces, right? We've learned that linear momentum of a system can be changed by the introduction of an external unbalanced force. Similarly, an angular momentum can be changed by an external unbalanced torque, okay? So what is the most common thing that people have to experience when they're talking about torque? It is the steering wheel, okay? It is the steering wheel. Torque is twisting action that produces rotational or change in rotational motion, right? And notice here we got F1, F2. Neither of them are negative. Why? Because you could easily rotate them around and be the same again, right? So literally none of them negative, right? And then the R here is the radius of the circle, okay? The R here is the circle right here, right? So when you're turning a steering wheel, right, the forces are equal going all around that circle, okay? Another good example of torque is using a wrench, right? Have you ever had that problem where you're trying to turn the lug nuts on your spare tire, right? When you're trying to change your tire and some fool had already tightened up your lug nuts so tight that you couldn't get them free, right? With your wrench, okay? And so the key or the secret, right, to that wrench is that you just need to make it longer. And so the thing that most people do is they'll get like a PVC pipe and they'll put it onto the wrench and then they'll push it and then it will break open the bolt, right? And the reason why that is because the longer the arm, right, the more force there is, right? You don't have to add as much force, okay? I see plenty of people just jumping on their lug wrenches trying to get the lug nuts off of their car, or I mean off their wheel, right? But it doesn't work because to really make that torque force stronger, you just need to make the lug wrench longer, right? And the easiest way to do that is to put a pipe on it and turn it that way, right? And if you're if you're in the cars, one of the things that mechanics all have is called a breaker bar, right? And a breaker bar literally is a wrench that's like 2 feet long, okay? And all it's used for is the breaking bolts, right? All it's used for is breaking bolts because it turns out that a lot of bolts on cars are super tight, right? They're super tight. I mean, you want them to be tight because that suck if you're driving down the road and your car was rattling and then the bolt fell off and you're like, where did this bolt come from? Right? That'd be a bad situation, right? So you want them tight. Not too tight, but you want them tight. So the thing I want you to notice here, right, is that as the length of the arm is doubled, the torque force is doubled, right? So as the radius, right, is doubled, the torque is doubled. So say you had that wrench and it was like a foot long, okay? Or say you had the lug wrench, it was a foot long, and it wasn't going to it wasn't going to break your lug nuts. But then you got a pipe and you made it 4 feet long, right? You've just added 4 times, or actually it would be 8 times because it's double, right? The amount of force you put on the lug nut. And now you just got to use a finger at the end and push it down. It will open. It will release lug nuts, right? Oh man, this like here you are changing your tires. You had no idea that it's all Newtonian, right? It's crazy, isn't it? So that's what I want you to remember, right? As the length of the lever arm is doubled, the torque is doubled. So, next question. In reference to torque, when you double the length of the lever arm, which of these is true? Man, I'm so excited. We're actually going to get through an entire lecture today. I don't think we've ever done that. Huh? Oh, that's why we got through it. It's because the quiz is at home now. I forgot about that. We saved like 20 minutes just from not taking a quiz in class. That's better, right? Because I know you guys. You'd rather have this lecture in class because you're, like I said, you're watching my lecture videos at home. It's just helping you sleep. So it helps me sleep. I listen to myself all the time to fall asleep. If you thought I was not narcissistic enough, right? I definitely listen to my own voice while I'm sleeping. I love re-listening to my lectures, especially my organic chemistry lectures. They're so riveting, so riveting. I'm like, what am I going to say next? Oh wait, I knew that I was going to say that because I said it. It's a good time, is what that is. Torque, 21 responses. I expect everybody to get this right. Yes, I'm so proud. Thank you. Thank you, Lord. They all got it right. Okay, the torque doubles for the given force. Good job. Very good job. Okay, so again, we have this law of conservation of angular momentum now, just like we had the law of the conservation of linear momentum. Remember that? Okay. And this says the angular momentum of an object remains constant if there's no external force or unbalanced torque or force about the axis acting on it, right? It's the same exact thing. It's the same exact thing as the linear momentum conservation law, except this time it's going in a circle, okay? Objects that go in paths around a fixed point, for example, a comet orbiting around the sun, okay? Okay. Very similar, very, very similar to your law of conservation of linear momentum, except this time it's in a circle. Okay. So let's talk about a very, obvious, very obvious example here, right? By the way, a lot of people think that the orbit of any mass around the sun, like the Earth or any other planet, is like completely circular. It's almost circular. It's actually elliptical, right? It's actually elliptical. And so at one point, the sun is like this far away, R1 away from the Earth. And then at some points in the year, the sun is R2 away from the Earth, right? R2 away from the Earth. But the interesting thing about it is that when when the Earth comes around this side and it's at the short end, right, it actually travels faster, okay? But then it comes around this side, right, and it actually goes slower. So since this side is going faster and this side is going slower and this side is smaller and this side is bigger, it still cancels out. The angular momentum is still the same. It's crazy, right? It's absolutely crazy. It's absolutely crazy, right? So the mass is constant. The planet's orbits are slightly elliptical. Therefore, both r and v will slightly vary during completion, right? As r changes, so must v, right? So when r decreases, v must increase, right? And so when you put it all together, going fast over here for a shorter distance, right, equals to what? Going slower over here at a longer distance. And the masses stay the same. Isn't that crazy? So there's this guy, his name's Kepler, right? And he came up with the laws of planetary motion, Kepler's laws of planetary motion. And he was the one that figured this out, right? He's the one that figured this out. Such awesomeness, that Kepler. Such awesomeness. All right, so let's just do a little quick example here, right? We have a comet, and at its farthest point, right, from the sun, it's 900 million miles, traveling at 6,000 miles per hour. What is its speed when it's closest to the point of uh, at its closest point of 3 million miles away? 30 million miles away, right? So the furthest point is 900 million miles, right? The furthest, and then the closest point is 30 million miles, right? And literally all you have to do is use this equation because we know it's all going to be the same for angular momentum, right? All going to be the same. You're given the you're given both of the radiuses, right? The far side radius, which is 900 million. You're given the short distance, the short side radius, which is 30 million, right? So that's both r's already. Okay. You're given the let's see here. Oh, You already know that the two masses are equal to each other, so you don't have to worry about that, right? And you're given the second velocity. So literally, you don't even have to worry about the masses. All you have to worry about now is the two velocities and the two radii, right? Plug them in, right? For the second rate, you're looking for the first velocity, right? Because it's asking you at the closest point, right? So that's the first velocity. So the second velocity goes here, right? And the second radius goes here. So the second radius and the second velocity are both the ones that are the furthest points, right? And then the distance that's the shortest point goes at the bottom, and you just do the math, right? Multiply these two to each other, divide by that number, and you get 1.8 times 10 to the fifth miles per hour, or 180,000 miles per hour. Man, that's a fast comet, right? So it's really simple. Like again, I'm not gonna. I might ask you to do something like this, but it won't be very complicated. It's literally just plugging in numbers or knowing the relationship between those different variables, right? And they're literally the same on both sides. So there's really no way to mess that up, right? Another example of this, right, is a Chinook, right? The Chinook helicopter, right, has two rotors, right? And both rotors are actually going in opposite directions. Tell me what would happen if they were both going the same direction? It would crash. It'd just go to like if it was turning to the right, like counterclockwise, both rotors. Then the entire helicopter would just go to the right all the time. It's like it's like a dog with like a gimp leg, always going in circles, right? You know, like that. That's what happened. That would happen to the Chinook, right? Back at Sam Houston, we had this dog named Tripod because he was missing a leg, right? And he was a dog that he went all over campus just begging for food. So the students at Sam Houston, we give him food, right? And literally, the guy was missing a leg, right? Tripod was missing a leg, his left leg to be exact. And when he literally ran towards the left all the time, all the time. Like you think I'm joking, but look it up, look it up. Like I mean, I'm sure there's something like that at Wesleyan. Don't you guys have a dog that does that? Huh? You have a squirrel that does that? Is that what you said? And they're missing a leg too, and they're running around in circles. Anyway, so that's why the Chinook helicopter can fly straight. It can fly straight because the rotors are going in opposite directions. Okay, they go in opposite directions. So again, here's another good example: conservation of angular momentum. Right, a figure skater, right? He or she starts to spin with his arm out with one velocity, but by simply pulling his or her arms in, the skater spins faster, right? Since the average radial distance is decreased, right? So when the figure skater is spinning like this, their arms are out, right? But if they want to get faster, they just pull their arms in and the radius is smaller, right? And that's why they start spinning faster. Does that make sense? It's the same thing that happens to the Earth when it's going around the sun, right? On the very short side, going faster because the radius is smaller. The exact same thing. Okay? All these phenomena are described, and they all over the place, and they all mean the same thing, right? Mass is constant, but the thing about it is that her mass may be constant, but the thing about her or him is that her radius decreases when she brings her arms in, and that makes her go faster. Okay? All right. So why does a figure skater spin faster when she pulls in her arms? I am so proud. We only have 2 slides left. This is what we should always do. Just have quizzes at home. If you're okay with that. Do you guys want quizzes at home? Is that better for you? Yeah? Do at the end of the day type of thing? Okay. Because I'd much rather stand up here and talk instead of like watching you just typing on your computers during a quiz. I mean, even though I feel like I'm talking a lot, but that's kind of like my job. So, all right. Let's see how people have answered this question. And then we'll go to our last slide. Torque. No, not torque. Figure skater, figure skater, figure skater. There it is. Everybody's responded. Uh-oh, what happened here? Not everybody answered correctly here, right? The answer is, in fact, C. Her arms went down, right, pulled together, so her radius decreased. That's why she gets faster, right? What the heck? Who picked A? Why would her mass decrease? Did she lose weight? Was spinning making her lose weight in the middle of the thing? Like, I wish I could just spin around in a circle and lose weight, right? She's definitely not losing. And then I mean, Jesus. Okay. All right. So the last slide, the last two slides are this, right here. These are the important equations you need to know, right, for the exam. But I'll provide them to you, okay, on the exam, along with like a formula sheet and scratch paper, right? And then these these are these equations are important too, but I'll provide them to you on the exam. And that ends your lecture. Hallelujah!